Hi, welcome to the tutorial about probability theories for cryptographies. Now we will take a look at this piece of code that I have here, and we will basically analyze what is the probability that this piece of code leaks the secret key. And this will be somewhat instructive for all of the other proofs that we're going to do in this course, because all of these techniques for handling probabilities, they will come up again and again. So this should help. Okay, let's take a look. So we have in this code here, we have multiple things going on. So first of all, you need to notice that we have two kinds of secrets. We have the secret key, which is a random integer between 1 and 2 to the 2 times k. So it's and in addition, we have a lesser secret, abbreviate L as k, and this is between 1 and 2 to the k. Okay, and then the following will happen in this piece of code. We have an error that initially is false. Then we have a query phase over here. Basically, the idea is that this runs on some sort of server, and we have an adversary that may be able to query this server multiple times. And whenever he queries it, he submits a guess. And if this guess is actually equal to the lesser secret, then some sort of error occurs. Okay, and then the error flag is set to true. Then the idea is that after this query phase, the adversary will call finish. And then, depending on all of the server state, the secret may or may not leak. Okay, so either the secret key is printed here or it isn't. So what does the adversary do? The adversary will basically query this query function multiple times with random integers between 1 and 2 to the k. And he does this n times, this n here. And then afterwards he calls finish and hopes that the secret key leaks. And now our goal is to show that the probability that this code outputs the secret key, that it's at most n times 2 to the minus n k plus 0.1. So what you can do is you pause the video, then you try to solve it yourself. You can use all of the stuff that I prepared for what kind of probability theory you need for this course. Everything you need is on there. You can try to solve this yourself, and then afterwards you can compare your solution to mine. Okay, so let's just solve it then. So what is the actual probability? This is what we want to look at. What's the probability that the secret key is leaked? And if we take a look at this condition here, where the secret key is leaked, we already can do some statements. So it seems to be conditioned on whether or not there occurs an error. Okay, so let's make it easier for us and let's do the first step and look at this probability in two cases. So we basically do a case distinction here. We look at the probability that the secret key leaks in case an error occurs, and the probability that the secret key leaks in case no error occurs. Okay, so we can write it down like this. So this is the probability that the secret key leaks under the condition that an error occurs, multiplied with the probability that the error occurs, plus the probability that the secret key leaks under the condition that the error does not occur, times the probability that the error doesn't occur. It's kind of like a standard way of writing our case distinction using essentially the law of total probability. So, and from the code we can already directly see what this is going to be. So this case distinction makes it way easier for us to analyze, right? So if let's say we have a run of this probabilistic thing and we know that an error occurs, which means that if we look at this condition here, we are in this case in front here where the error occurs. And this thing here doesn't matter to us right now. Okay, so what we can see immediately is if the error occurs, then the probability that the secret key leaks is just this here. So it's 0.9. And similarly, if the error does not occur, we know that the probability that the secret key leaks then is given by this part here, and this is just 0.1. Now it makes sense to look at what's the probability that the error occurs, because this is still left for us. So what's the probability that an error occurs? If we look at the code, we see that an error occurs if one of these guesses is successful, and we have multiple of those guesses. So the probability that the error occurs is just the probability that of the event that any of these guesses is successful, which I will call error I to mean that the ith try is successful. And then I can write the probability that an error occurs as the probability as like a big OR over x between, I guess, 0 and n minus 1. So n in many of those, that the xth try succeeds. Okay, so this is a big OR, multiple ways this can happen. So this is kind of unwieldy, that doesn't help us too much at first. But thankfully in probability theory, we have this nice inequality that tells us something about like the OR of multiple events. In particular, if we have like multiple very unlikely events and we just want to upper bound that any of them happen, we can just use the union bound. The union bound then tells us that this is at most the probability, this is at most the sum of all of these individual probabilities. And now this makes it a lot easier, because now we're just left looking at each of these probabilities for the xth try individually. And this makes it easier, okay? Because now let's actually do this. The probability of the xth try is just the adversary chooses a random integer between 1 and 2 to the k. And this lesser secret here, well, he doesn't know it, or actually it doesn't matter whether he knows it or not. He chooses a random guess, so the probability of him hitting the lesser secret exactly is just 1 over 2 to the k. Overall, we then sum up a bunch of 1 over 2 to the k's. And how many summons are there? There are n summons. So in the end, we get n over 2 to the k. So this is nice. Now we have learned that also the probability that an error occurs, this is at most n over 2 to the k. Okay. And now we're basically done. The last thing that we would need to look at is this probability that the error does not occur, which we can't get to easily, right? Because it's not the inverse of this anymore, because this is only an inequality. So we don't actually, it's not easy to get the exact upper bound for the fact that no error occurs. But you know what? We don't need an exact one. We can just notice that this is at most 1, and then just remove it from the equation. Okay, so overall, this actually gives us the bound that we were looking for. So what did we learn? We learned that things become much easier if we do like case distinctions for our probability problems. We will do this in the lecture a bunch of times. And then also if there are events that happen with small probability, then usually we don't need to know the exact bound for them, but we can just look at the union bound and take this inequality here, and this suffices. We often have the case that an adversary can try to guess something, also in our proofs that we will do later. But we will know that like the probability of succeeding is very, very small. So if he just tries a polynomial number of times, we usually don't care then. Okay, that's it for this. Thanks for your attention, and see you.